So this is a lecture 17 part C, so network theory. In this lecture we are going to see what is the maximum power transfer theorem. In lecture 17 we have seen three theorems, that is superposition, Thevenin's and Norton's theorem, and how to find the response in a particular branch when so many independent sources, so many resistance are there, right, and dependent sources. In part B I have solved some questions on these theorems, and also I uploaded the lecture notes and problem sheet with solutions. So in this problem sheet I have taken from the fundamentals of electrical circuits by Sadiku. So many problems that are there, so I have taken some problems and I have given for approximately 10 questions or 11 questions solutions also. So see the solutions and do practice on your own for the remaining problems. So these lecture notes and this problem sheet and solutions I uploaded in our blog, that is learningiseverything.blogspot.com. So you can download and see the solutions. Is there any mistake or wrongly calculations done? So please comment on that session. So in blog or in this YouTube channel, right? Next we will see what is the maximum power transfer theorem. Now what are the limitations or where we can apply this theorem is, it is applicable only when the load impedance is variable. If the load impedance is not variable, if it is fixed, what is the condition? If the load impedance is fixed, choose the minimum impedance path that cause maximum current flow through the load. So what is this actually meaning is, suppose you are having some load, right? Now, and if you know the current, load current and the load impedance, so what is the power actually? I square into the impedance, or we can say simply R. Now how can I get maximum power? Two conditions, V square by R also. If I is maximum, then we can get maximum power. If V is maximum, we can get maximum power. So two conditions. That means if this load is varies, so we can find what is the condition which will goes through maximum power, right? If suppose this is fixed, now we have to choose the internal impedances like that this IL will be maximum, then only we can get maximum power. So that are the two conditions. If this is variable, then we can apply this theorem and we can find the what is the condition. If it is fixed, so we have to choose the minimum impedance path that causes the maximum current flow, then only we can get the maximum power to the load, or we can transform the maximum power to the load. Next we see what are the limitations. So limitations is nothing but for which circuits we can apply this theorem. Always it is applicable only for linear circuits. We have seen all the theorems which is applicable to all linear circuits only. Now it can be active and as passive circuits, no problem. So it can be consist of passive elements, active elements. So for that circuits we can apply the maximum power transfer theorem.
Cases in maximum power transfer theorem. So we are seeing case 1. In case 1, suppose the voltage source, so we can represent either source voltage as VC, VS, or the Thevenin voltage VTH. And similarly, if it is a purely resistive, so I can replace RS or Thevenin resistance RTH. And this is also pure resistance, that is load resistor RL, which is variable. Now we will find the conditions to deliver maximum power to the load. So the source should be deliver maximum power to the load. So what is the condition? Now if I know this current, suppose I am assuming as some current IL. Now by definition, Ohm's law, what is IL? The voltage, that is VS or VTH. So I am taking it as VS by total resistance RTH plus RL. Equation 1. Now I need a load power, so I am assuming as PL. So PL, if I know the current, so I can easily find the power IL, I square into R. So IL square into RL. So what is IL? VS square by, so RTH or simply RS also. So RS plus RL square into RL, because IL square, VS square by RS plus RL whole square. So I can replace RTH by RS also, no problem, right? So this is the condition or load or P. So second. Now to find the maximum power, so we need to differentiate the load power with respect to the variable, that is here load resistance RL. So if you see, this is U by V formula we need to use. So differentiation, so V square, that is RS plus RL square already there, so again square means we will get RS plus RL power 4. Now V, that is RS plus RL whole square into differentiation of U, so Vs square will be there and RL means 1 minus Vs square into RL. If I differentiate this square term, so I will get 2 times of RS plus RL. Now to find the maximum power condition, or to find the maximum power value, so we need to equate this term into 0, so equate to 0. Now if I take common Vs square, so here I'll get RS plus RL whole square minus 2RL into RS plus RL is equal to 0. Now Vs cannot be 0 because this is a source voltage. So what is the other terms? This term will be 0. So if I take RS plus RL common here, so we will get RS plus RL minus 2RL is equal to 0. So what is this? RS plus RL into RS minus RL. So A plus B into A minus B, that is RS square minus RL square is equal to 0. So this represents RS is equal to RL. Now this is the condition to deliver the maximum power. That is if the load resistance RL is equal to the source resistance RS, then the source will deliver maximum power to the load. This is the condition for maximum power to the load. Now if I substitute in substitute RS is equal to RL in equation 2, that is to find the load power PL. So PL max is equal to Vs square into RL by, so in place of RS plus RL, so it will become 2RL square. So 1RL will be cancelled, so it is Vs square by 4RL, or this is also can be represented by Vth square by 4RL, or it is represented by Vth square by 4RS also, or RTh also, right? So it can be Vs square by 4RS or Vs square by 4RL, so whatever same values we will get. So this is about the maximum load power. Now if I find the efficiency of this circuit or this condition, so eta is equal to the load power by the total power. So what is the load power? Just now we have seen, that is Vth square by 4RL or Vs square by 4RL. The total power means the total current square, that is I. So same current is flowing in this loop, so IL square into the total resistance is RS plus RL, right? Now again we need to substitute this IL square like this. So this is Vth square by 4RL by IL means again Vth or Vs square by RS plus RL square into RS plus RL. So 1 will be cancelled here. So what we will get? So I'm writing here. So we'll get, so Vth square will be cancelled. RS plus RL by 4RL. Now since RS is equal to RL, so we'll get 2RL by, this is RL, 2RL by 4RL. It's nothing but 50% is the efficiency, right? So the remaining 50% will be dissipated across the resistances, right? So that is about the maximum power condition when both are in resistive. Next we will see when both are in complex in nature. So before that I will give one graph. So if I vary this resistance RL, so what happens to the load power PL? Now it is slowly increasing and at RL is equal to RTH or RS. Now we'll get maximum power, that is PL max, and after this again it will decreases. So only we'll get at the maximum here is, this is the condition, when RL equal to RS we'll get maximum. Other than this, other below or greater than this, we'll get the power will be reduced. So remember this graph that is required. Now case 2, now the complex, that is Zs is equal to Rs plus J into Xs, and here also Zl is equal to RL plus J into XL, and here we'll have AC source, that is I am considering Vs, which is AC source. Now whenever there is a complex impedances, we'll have AC sources always. Now when this is the conditions, how to find the this load power, PL max, etc. What are the conditions? Now remember, whenever there is a complex, so we'll find the magnitudes, right? So PL is equal to, so either VL into mod of IL, or we can say VRMS into IRMS, right? Or VRMS into IRMS, right? Or we can say mod of IL square into RL, or mod of VL square by RL, etc. Now before that, so we'll see when RL is having, ZL is having impedance as well as the reactance, resistance or the reactance. Now part A will come like this. If RL is variable and XL is fixed, right? And the second case B, RL is fixed and XL is variable, right? Now third condition is both RL and XL are variable, right? Now one by one we have to see. Now case 1, I'm taking RL is variable and XL is fixed. Now how to find the, now same procedures, IL is equal to the source Vs by total impedance generally, so it will become Rs plus RL, imaginary part, that is J into Xs plus XL. Now I told we need to take the magnitude, so if I take mod IL, it is Vs by Rs plus RL whole square, real part square plus imaginary part square and square root. So this is the equation 1. Now we need power calculation, so PL is equal to mod of IL square into RL. Now only we need to see the load power, which is we need to deliver, right? Only dissipating power, not storing power. So this is mod of IL square into RL, equation 2. Now to find the maximum power, so differentiate with respect to RL, right? So before that, write the mod of IL square. So IL means Vs by Rs, so mod square means Vs square by Rs plus RL whole square plus Xs plus XL whole square into RL. Now we need to differentiate this expression right here. Now next, dPL by dRL with respect to RL, because RL is variable, right? Now again it is U by V formula, so V square, that is Rs plus RL whole square plus Xs plus XL whole square and whole square, V square, so V is this one. Again same value will be here, Rs plus RL whole square plus Xs plus XL whole square into Vs square into, with respect to RL means 1, minus Vs square into RL will be here. So here if you see, Xs plus XL is the fixed one, so it will be constant, so it will be 0, so it will become 2 into Rs plus RL, which is equal to 0. So I'm going right directly, Vs square cannot be 0, so the remaining term will be 0, that is Rs plus RL whole square plus Xs plus XL whole square minus, so if I multiply 2 into RL into RS minus 2 RL square equal to 0. So if I expand this one, RS square plus RL square plus 2 RS RL plus XS plus XL whole square minus 2 RL RS minus 2 RL square equal to 0. 2 RL rest will be cancelled. Now in place of RL square minus, so it will become RS square minus RL square plus XS plus XL whole square equal to 0. So minus RL square, that side is going, so RS square plus XS plus XL whole square, which is equal to RL square. Now what should be RL? So RL is equal to square root of RS square plus XS plus XL whole square. So this is the condition to deliver maximum power to the load, right? Now again, if I find the PL max, so we'll get same as Vs square by 4 RL, but RL is here RS square plus XS plus XL whole square. So this is the about the part A in the second condition. Next we will see part B, that is RL is fixed and XL is variable. Now in this case also, so that is PL is equal to Vs square by same condition, that is RS plus RL whole square plus XS plus XL whole square into RL, because dissipating power we need, so only resistance will dissipate the power, so we can take same exact equation. But if XL is variable, that is we have to differentiate this expression with respect to XL. Now if you see, the numerator is constant and the only denominator is having XL, right? It is 1 by X formula, so minus 1 by X square, that is minus Vs square into RL by RS plus RL whole square plus XS plus XL whole square. Now I have assumed this is X, so into, we need to differentiate this one, so this is 0 plus 2 into XS plus XL is equal to, this is the differentiation. So to find the maximum, we need to make it 0. If this is going that side and Vs cannot be 0, only we will get XS plus XL equal to 0. That means the XS or XL should be equal to minus XS. That means the imaginary part in the here, if both are complex conjugate, so it will be cancelled, so only will have the resistance, only resistance part, right? Or the network should be, or it will be a resistive network, purely resistive network, right? So that is the power dissipation, that is again PL max is equal to Vs square by 4 into RL, and here what is RL is nothing but RS, because XL is equal to minus XS. So in the previous expression for the case D, we got RS square plus XS plus XL whole square, so this will become 0, so RL is equal to RS, right? So this is the condition 2, this case 2 part B. And the last one is both are variable, right? So part C, so RL and XL are variable. So we have to add both conditions at a time, that is if RL is variable, so we know RL equal to RS square plus XS plus XL whole square. If XL is also variable, XS is equal to minus XS. So if I substitute here, what you will get, RL is equal to RS. That means RS plus J into XS is ZS should be equal to RS minus J into XS, which is, we can say, this is RL this is J into XL. So, or we can say conjugate. So ZL is equal to ZS conjugate, right? So RL is equal to RS, XL is equal to minus XS. So RL minus J into XL, etc. So ZL is equal to ZS conjugate. Then also the maximum power is equal to Vs square by 4RL. See, this power condition doesn't change in any case. Vs square by 4RL. So only RL value changes. Now I will summarize here all the conditions. So we will look after that. So summary. So case 1, if RL and RS both are in resistive, so RS should be RL, and the maximum power PL is equal to Vs square by 4RL. Now in second case, ZS, and in ZL only RL is variable, right? When RL is variable, so RL is equal to square root of RS square plus XS plus XL whole square, and the power is again same, Vs square by 4RL. Next condition, ZS, and in ZL XL is variable, right? When XL is variable means, so we'll get XL is equal to minus XS. When it is minus XS, what is the power? PL, VL square by 4RL, and RL here is RS. Now the last condition, ZS and ZL, that is RL comma XL, both are variable. So both are variable means same, RS is equal to RL and XL is equal to minus XS, both conditions at a time. So we'll get, or we can say ZL is equal to ZS conjugate, complex conjugate, and the power PL is equal to Vs square by 4RL. So this is about the maximum power transfer theorem, right?
Now see, determine the value of RL that will draw maximum power from the rest of the circuit. Calculate the maximum power. To derive or find the maximum power or the resistance, what we need to do is, wherever we want, just open the circuit there and apply a Thevenin voltage VTH. Then find the VTH and RTH. Now, how to find VTH? The moment when we open, what is the current here will be 0. That means this is a drop here 0. So directly we will get VTH here. Now if you apply nodal analysis, so VTH minus 9 by 2 plus VTH minus 3Vx by 1. So this is current is 0. So directly 0. Now if we take VTH common, this is 1 by 2 plus 1. So 3 by 2. Now minus 3 into Vx is equal to 9 by 2. That is 4.5. Equation 1. But we need Vx. Now if you see here, this is the total voltage VTH. And if you apply this KVL, what I will get? 9 minus VTH is nothing but Vx. So Vx is equal to 9 minus VTH. If you apply KVL, you will get like this only. Now if I replace here, what I will get? If I take VTH common, so 3 by 2 minus half minus, so it will be plus 3. I am taking directly common, and minus 3 into 9, so 27. It is going that side. 4.5 plus 27. Now if you solve this one, we will get 7 volt as the Thevenin voltage. Similarly, what we need to find? Right? The resistance value. So to find the resistance value, so there are so many ways. So we have to find the short circuit current, then VTH by AC. Another way is make all independent sources 0, that is source voltage is 0. This is 2 ohms, and this is plus minus Vx, and this is 1 ohm, and this is plus minus 3 Vx, and this is 4 ohms, and this is where we need to find the Thevenin. So I will apply a test voltage and test current. Now if I find Vt by It, so I will get RTH. Now how to find that one? So we will do the derivation something like this. So again, always very helpful is nodal analysis. So I will apply voltage V. Directly I am writing V by 2 plus V minus 3 Vx by 1 plus, see this IT is incoming, so I will assume as outgoing, so minus IT equal to 0. So 1 by 2, that is 3 by 2 V minus 3 into, again what is Vx? So if you see this one, if you apply KVL, this total voltage is V. Now if you apply KVL, plus Vx plus V equal to 0, that means V is equal to minus V. So I am applying, see, since V is equal to minus Vx, see here, so this is, if you make like this, so plus V is equal to minus V, so parallelly the voltage should be same, so that's why V is equal to minus Vx is equal to IT. So what is this one? Plus 3, so it is 4.5 V is equal to IT, but we need expression in terms of Vt and IT. Now what we get? So this is the voltage V. If you apply the KVL here, we will get the Vt. So Vt is equal to 4IT plus V. See here, this is the V. So minus Vt plus 4IT plus V. So it will be going that side. So Vt is equal to this voltage plus this voltage. Right? Now what is V here? So V here is, so I will apply 4IT plus V means IT by 4.5, right? So this is the Vt. So what is you will get? So if I take IT common, 4 plus, so I think it is 2 by 9, this is Vt. So we'll get Vt by IT as 4 plus 2.9, right? Approximately 4.22 ohms. We'll get the RTH. Now if I replace this circuit, total circuit, simply plus minus 7 volt, this is 4.22 ohms, and this is RL. Now we know what is the maximum power theorem tells. If RL is equal to RS, that is 4.22 ohms, then it is the maximum power it will deliver. So what is the PL max? V square, that is Vs square by 4RL, that is 7 square by 4 into 4.22. So what is the approximately you can get here is I think 2.9 watts. This is the maximum power to the load. So this is how we do the derivations or solve the questions like this. Similarly, it can be J into XL or what you call total JL, RL plus J into XL, depending on this one. So that will do problems in the next session. One more problem, the very important, which is I think this is the previous gate question. We need to find R. What value of R will give maximum power across the 3 ohm resistance? Now see, this is the 3 ohm resistance, means RL is fixed. Now in this case, what is the R should be, then it will deliver maximum power. So options are given like this: if R is equal to 0, if R is equal to 6 ohms, if R is equal to 3 ohms, and D not possible, etc. Right? Now how to do this type of problem is, I told we have to choose the minimum resistance path. If RL, so we will do the reverse operations. That first case I will put R equal to 0. What will happen? If the moment R is 0, it is short circuit. So short circuit parallel with resistance, you will get short circuit only. That is 20 volt. This short circuit. What is this 3 ohm? Is this one. What is IL? IL is equal to 20 by 3. Now what is the PL? 20 by 3 square into 3. What we will get? 400 by 3 watts. This is the first case. Now second case, suppose if R is equal to 6 ohms. So 6 ohms, 6 ohms. So we'll get 3 ohms. So that is plus minus 20, and this is the 3 ohms, and this is 3 ohms. Right? Now what is this current IL? IL is equal to 20 by 6. That is 10 by 3 amperes. Now what is the power, maximum power load? 10 by 3 square into 3. So it is 100 by 9. So 100 by 3 watts. Right? Next one. C is equal to R is equal to 3, suppose. Now 3 parallel 6, so we'll get 2 ohms, right? So this is 2 ohms and this is 3 ohms. This is plus minus 20 volts, and if I see what is the current here, I will get 20 by 5, so 4 ampere. So what is this current? IL. So what is the power P? IL square into that 3 ohms, so 16 into 3, right? 48 watts. Now if you observe these these problems, which one giving is the maximum power? The 400 by 3, right? This is the maximum power, 100 by 3, and this is 48 only, right? So which is the resistance which will give maximum power? Is nothing but R is equal to 0. So what is the option? R equal to 0. Sometimes, some other cases, it may not be R equal to 0. For that reason, or in that cases, substitute R, then find the maximum R power. Now whichever the case is giving maximum power, that is a R, right? So that's why we have to choose the minimum impedance path, right? So that is about this one. Next we will see the problems on this maximum power in the next lecture.